Hello everyone, welcome to the lecture of this course heat transfer. So this is the continuation of the last lecture of this radiation module where we have discussed the heat exchange between the non-black bodies or non-black surfaces. So there we have discussed the formula for the net radiant heat exchange, and for the interchange factor we have seen those different configurations are having their own formula for the interchange factor, so which was represented in a tabular form. So those formulas that we have discussed in the last lecture, that based on those formula today we will discuss different numericals and one electrical analogy for the thermal resistance, that also we'll discuss today. Okay, so let us start this lecture. So these are the things that we have discussed in the last lecture, so I will just quickly skip this slide. Okay, so these were the table that we have discussed mainly in the last lecture, and all the formulas are here that we will use today to solve the numericals. So up to this table we have discussed in the last lecture, so we will continue from the next slide today. So this is actually the electrical network analogy for the thermal radiation system. So in case of the conduction and convection, we have seen the thermal resistance concept. So similar type of concept for the radiation heat transfer we will discuss. So this electrical network analogy, it is actually the alternative approach for analyzing radiation heat exchange between the black or gray bodies or black or gray surfaces. So two different terminology, that is irradiation or incident radiation and radiosity. So these two things will be very much useful for this electrical network analogy. Now these two terminology, that is irradiation and radiosity, these are already discussed in this first lecture of this radiation module, where we have seen the different surface emission properties. So it is known to us that the irradiation or incident radiation, which is denoted by capital G, this is actually the total radiation incident upon a surface per unit time per unit area. So this is the definition of irradiation or incident radiation, and its unit is capital watt per meter square. And the radiosity, that is capital J, this is actually used to indicate the total radiation leaving a surface per unit time per unit area, and it is also having the same unit as irradiation. Now this radiosity formula, it is actually comprised of the original emittance phi from the surface plus the reflected portion of any radiation incident upon it. So that means the mathematical representation of this radiosity, it is actually capital E plus rho g. Now from the concept of the emissivity and emissive power, we can write this capital E equals to emissivity multiplied by the emissive power of a black body plus rho g. Now from our earlier discussion, we know that there is a relation in between the absorptivity, reflectivity and transmissivity of a body, and which is that the summation of these three properties, these are actually 1. Now here, as the surface is opaque, that means the transmissivity is 0. So in that case, only the absorptivity plus reflectivity, this is equals to 1. So that means the reflectivity, this is equals to 1 minus alpha, that is 1 minus absorptivity. Now if we put this value of this rho, that is reflectivity, in the equation of radiosity, so in that case we are getting the representation of radiosity, this is equals to epsilon EB plus 1 minus alpha into capital G. G is the irradiation or incident radiation. Now if we apply the Kirchhoff's law, which states that the absorptivity, this is equals to emissivity. So if we put this formula of the emissivity or absorptivity here by using the Kirchhoff's law, then the representation of this radiosity, this is actually J equals to epsilon EB plus 1 minus epsilon into G. So here you can see that the diagram that we are discussing now, that the capital G, that is the irradiation or incident radiation that is falling on the surface per unit time per unit area, and this J, that is the radiosity which is leaving the surface per unit time and per unit area. And this non-black surface, it is considered as an opaque body, that means the transmissivity tau equals to 0. Now from the equation of the radiosity, we can get the formula of the irradiation, capital G, this is equals in terms of radiosity and the emissivity, this is that is G equals to J minus epsilon EB divided by 1 minus epsilon. So that is equation number 12.30, and it is the representation or the formula of the irradiation or incident radiation for an opaque and non-black surface. Now the net energy leaving a surface is the difference between its radiosity and irradiation, which can be seen in the diagram 12.23. And based on this diagram, the electrical circuit is also prepared here. So if the net energy leaving a surface is the difference between the radiosity and irradiation, so in that case Q net divided by area, this is equals to the radiosity minus the incident radiation or irradiation, that is J minus capital G. If we put the formula of capital G here, then after some steps we are getting the Q net, this is equals to EB minus J divided by 1 minus epsilon divided by A epsilon, that is the equation number 12.32. Now the representation of this equation in the form of electrical network, it is seen here in the 12.23b. So here you can see in the black emissive power of the perfect black body, it is there, and the radiosity is also there. Q net, it is represented, and the electrical network circuit, here the resistance is written as, the formula for the resistance, it is written as 1 minus epsilon divided by A epsilon. Now this quantity 1 minus epsilon divided by A epsilon, this is actually known as the surface resistance. So this formula for the surface resistance we need to remember. So this surface resistance, it is related to the surface properties of a radiating body. So this is the concept of the surface resistance. So next, let us consider the exchange of the radiant energy. It is between the two surfaces 1 and 2. And now of the total radiation which leaves the surface 1, the amount which reaches the surface 2, it is now J1 A1 F12. Now similarly, the heat radiated by surface 2 and received by the surface 1, it can be represented as J2 A2 F21. Now the net interchange of heat between the surfaces Q12, this can be written as Q12, this is equals to J1 A1 F12 minus J2 A2 F21, which is equation 12.33. From the concept of reciprocity relation or reciprocity theorem, we can write that A1 F12 this is equals to A2 F21. So that means the Q12 this is actually the A1 F12 multiplied by J1 minus J2. So it can be represented in this form also, that is equation number 12.34. So the equation number 12.34, it is represented in the form of electrical network in figure number 12.24. So here you can see in this electrical network circuit J1 and J2, the two different radiosities are here. Q12 that is the net interchange of heat between the two surfaces, and the resistance, its representation is 1 by A1 F12. Now this quantity 1 by A1 F12, this is a resistance and it is known as the space resistance because it is due to the resistance and geometry of the radiating bodies. Okay. So in this electrical network analogy till now we have seen that two different resistances are useful, and one is the surface resistance and another is the space resistance. So for the surface resistance, it is related to the surface properties of the radiating body, and the space resistance, it is due to the distance and geometry of the radiating bodies. So the formulas for these two different resistances, that is surface resistance and space resistance, we need to remember to solve the numerical problems. Now if the surface resistances of the two bodies and space resistance between them, if it is considered, then the net heat flow can be represented by an electric circuit. So which can be seen in figure number 12.25. So here we have considered the surface resistances for the two bodies and the space resistance in between them. So the net heat exchange between these two gray surfaces, it can be written as Q12 this is equals to EB1 minus EB2, which is the emissive power of a perfect black body 1 and 2, that is EB1 and EB2. Now if we multiply the numerator and denominator by A1, then after some steps we are getting Q12 net is equals to FG12 A1 sigma multiplied by T1 to the power 4 minus T2 to the power 4. So that means we are getting the formula for this FG12. This is actually known as the gray body factor. So this representation for the FG12, this is equals to 1 divided by 1 minus epsilon divided by f1 minus epsilon 1 divided by epsilon 1 plus 1 by f12 plus 1 minus epsilon 2 divided by epsilon 2 multiplied by a1 by a2. So this formula of the gray body factor we also need to remember to solve the numericals. So earlier we have seen the shape factor, after that we have seen the geometric factor, then interchange factor. Now we have got one more factor that is known as the gray body factor. So all the formula for the different geometrical shapes for these different factors we need to remember to solve the numericals. Now when the heat exchange takes place between two black surfaces, then the surface resistance becomes 0, as epsilon 1 equals to epsilon 2, this is equals to 1 in case of a black surface. So in that case the gray body factor, its representation can be written as F12, that is the configuration factor, and the equation then for the net heat exchange in case of the black surface it can be written as F12A sigma T1 to the power 4 minus T2 to the power 4. So this is the case of the net heat exchange equation in case of the black surfaces. When the gray body factor, it is equals to the configuration factor or shape factor. Now there are three different cases, and for these three different cases we will see that how the gray body factors equation gets changed. So the first case is when the radiating bodies are infinite parallel planes. So in case of an infinite parallel planes, the area this will be same, and F12, that is the configuration factor, this is equals to 1. So the gray body factor, it is ultimately represented as 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is the representation of the gray body factor when the radiating bodies are infinite parallel planes. So the second case is when the radiating bodies are concentric cylinders or spheres. So in that case F12, this is equals to 1. So this concept we know from the shape factor algebra. So the gray body factor in case of this concentric cylinder and concentric sphere, it can be represented as 1 by 1 minus epsilon 1 by epsilon 1 plus 1 plus 1 minus epsilon 2 epsilon 2 multiplied by a1 by a2. Now in case of concentric cylinder, a1 by a2, this is equals to d1 by d2, is the ratio of the diameter, ratio of the radius. And in case of the concentric sphere, the ratio of the area, this is equals to the ratio of the radius square, is r1 square divided by r2 square. The third case is when a small body, it lies inside a large enclosure. Now when a small body lies inside a large enclosure, in that case F12, that is configuration factor, this is equals to 1. And as the body, small body, it is very small, then in that case A1, it is much smaller than A2. So in that case A1 by A2, it will tends to 0. So that means the gray body factor equation for a small body lies inside a large enclosure, it will be 1 by 1 minus epsilon 1 by epsilon 1 plus 1. Okay, so these are the values of the gray body factor for the three different cases, considering the radiating bodies are infinite parallel planes, or the radiating bodies are concentric cylinder or sphere. In the last case is a small body lies inside a large enclosure. So the examples may be a pipe carrying steam in a large room, and a thermocouple bed located inside a duct to measure temperatures of the fluid of this radiant heat exchange. Now let us discuss the numericals based on the formula that we have discussed for this radiation module. A lot of formulas we have seen, starting from the reciprocity relation, the salient features of the shape factor, then the interchange factor for different configurations in case of a black body or in case of non-black body. Then from the electrical analogy, today we have seen the space resistance, surface resistance, then the gray body factor, and how the gray body factor gets changed for three different cases. So a lot of formulas we have discussed. Now based on all those formulas, let us try to solve some numericals. So the question says, determine the rate of heat loss by radiation from a steel tube of outside diameter 70 mm and 3 meter long at a temperature of 227 degrees centigrade if the tube is located within a square brick conduit of 0.3 meter height and at 27 degrees centigrade. The emissivity for the steel, it is given as 0.79, and emissivity for the brick, it is given as 0.93. The diagram is given here for the steel tube and for the brick conduit. Now we need to determine the rate of heat loss by the radiation. Now the heat transfer, it is given by the formula, that is Q equals to A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon plus 1, epsilon 1 plus 1 by epsilon 2 minus 1 multiplied by A1 divided by A2. Now in this case, the ratio of the areas for these two different surfaces, it will be pi dl divided by PL. So this is actually ultimately 0.183. So the final value for the rate of heat loss by radiation from a steel tube to the outside, from a steel tube, so it can be calculated by putting all the formula, by putting all the values. Some of the values are given in the numerical, and the ratio of the area we have calculated just now. So if we put all these values, we can calculate the rate of heat loss as 1589.7 watt. So this type of numerical, these are very much simpler. Let us discuss the next numerical. So a hot ingot casting 25 centimeter by 25 centimeter by 1.8 meter at a temperature of 1200 Kelvin is stripped from its mold. The casting is made to stand on the end on the floor of a large foundry whose wall, floor and roof can be assumed to be at 290 Kelvin temperature. Now, if the emissivity of casting material is 0.8, calculate the net heat exchange between the casting and the room. So here the net rate of radiant heat exchange between the ingot and the room, which can be represented in terms of the gray body factor, that is Q12, this is equals to Fg12 A1 sigma T1 to the power 4 minus T2 to the power 4. Now first we need to calculate the area of the ingot. So it can be calculated by using the formula, and the value we are getting is 1.86 meter square. Now here from the question we can say that this type of configuration, it is a completely enclosed body and the small compared with the enclosing bodies. So in that case, this is actually the case that we have discussed in case of the gray body factors. There we have discussed three different cases, and for the last case, when a small body lies inside a large enclosure, in that case the formula of the gray body factor has been changed, where f12 this is equals to 1 and a1 is much lesser than, smaller than a2. So in that case, the representation of the gray body factor, it was ultimately 1 divided by 1 minus epsilon 1 by epsilon 1 plus 1. So see, this is the case, that is equation number 12.40. So this is the case we are dealing here in this numerical. So if we can remember this formula for the gray body factor for this specific case, then we can directly write this formula. So ultimately this Fg12, that is gray body factor for this case, this is equals to epsilon 1, and this value is actually 0.8. If we put this value in the net radiant heat exchange equation, then we are getting the Q12, that is the net heat exchange between the casting and the room. This is actually 174.58 kilowatt. So this is the procedure where we have calculated the net heat exchange using the formula of the gray body factor. So if you can remember the formula for this specific case, you can directly use this formula. So let us discuss the next numerical. An enclosure is formed by three surfaces. The diagram you can see here. the cylindrical enclosure. Now one table is given where the details of the shape factors, emissivities and temperatures are given. That is, three different shapes for the cylinder have been considered, and for the curved cylindrical, the emissivity and temperature is given, one enclosing disk and the other enclosing disk. So for these three different surfaces of the cylinder, it is represented as 1, 2 and 3 in the diagram. For these three different surfaces, the emissivities and temperatures are given. Now we need to determine what we need to calculate: the net rate of radiant heat flow leaving from surface 1 and reaching to each of the surfaces 2 and 3. Okay, so this is the thing that we need to find here. The diameters of two closing flat disks and interspacing between the two are 25 mm and 100 mm respectively. Now here we need to use the concept of the shape factor algebra. So what are the things given here? That is, the diameter d equals to d2 equals to d3, this is equals to 25 mm, that is 0.025 meter. The height of the cylindrical surface, it is h equals to 0.1 meter. f23, this is given 0.05. It is the shape factor between the two identical disks. And epsilon 1, it is given 0.8, epsilon 2 and epsilon 3, these are equal, that is 0.85. And the shape factor relations, that is f21 plus f23, this is equals to 1. So f23, it can be written as 1 minus f21. Again f12 plus f13, so this is equals to 1, so that means f13, this is equals to 1 minus f12. Again the reciprocity relation, this is equals to a1 f12, this is equals to a2 f21. And from this equation we are getting that f21, this is equals to 0.95. Now if f21 equals to 0.95, so that means f12, this will be equals to 0.059, putting in the formula of the reciprocity relation. Now q12 equals to q13 here. So there is no heat flow from 2 to 3 or 3 to 2, as q23 equals to q32. So that means q12, the net radiant heat exchange between the two surfaces 1 and 2. The formula is written as sigma T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by A2 epsilon 2. The area for the circular surface, it is area for the cylindrical surface, it is pi dh, and area for the circular surface, it is pi d square by 4. And temperature T1 and T2, these are given, which has been written in Kelvin unit. Now if we put all the value in Q12 equation, then ultimately after some steps we are getting the value as 3.376 watt. So this is the value of the net rate of radiant heat flow leaving from surface 1 and reaching to each of the surfaces Q23. As Q12 equals to Q13, so that means Q12 value 3.376 is equals to same as Q13. So in this way we need to solve the numericals based on the radiation concept. We have started by the concept of the shape factor, we have used the reciprocity relation, then we have used the formula for the shape factor algebra. After that, the net heat flow or net radiant heat exchange equation for this specific shape we have used here. So Let us discuss another numerical to calculate the heat transfer rate per meter square area by radiation between the surfaces of two long cylinders having radii 100 mm and 50 mm respectively. The smaller cylinder being in the larger cylinder. So this is the case given here. The axes of the cylinders are parallel to each other and separated by a distance of 20 mm. The surfaces of inner and outer cylinders are maintained at 127 degree centigrade and 27 degree centigrade respectively. The emissivity of both the surfaces is 0.5. Okay, so it is given that we need to assume that the medium between the two cylinders is non-absorbing. So what are the data given in this question? That is R1, this is 50 millimeter, 0.05 meter. R2 equals to 100 millimeter, that is 0.1 meter. The temperature for these two different surfaces can be written in Kelvin unit, that is 400 Kelvin and 300 Kelvin. The value of the emissivity for these two different surfaces, these are given as 0.5. Now, the heat transfer between the two concentric cylinders, the formula we have discussed earlier, so that formula we need to use here. Q1 to net is equals to A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 minus epsilon 1 by epsilon 1 plus 1 by F12 plus 1 minus epsilon 2 divided by epsilon 2 multiplied by A1 by A2. Now here F12 this is equals to 1. As per our concept of the shape factor algebra, we can write this, and A1 divided by A2, that is the ratio of the area for these two different surfaces. This is actually the ratio of the diameter or radius. If we substitute or if we enter these values in the formula, then we can get after some steps, that is the final value of this heat transfer between the two concentric cylinders. This is coming as 396.9 watt per meter square. So this is the final answer here in this numerical. We have to remember the formula of the net heat transfer rate for this specific shape of the object or body, and then we need to use the concept of the shape factor algebra. So let us discuss one more numerical, that is the question given is three hollow thin walled cylinders that we can see in this diagram also. Three hollow thin walled cylinders are considered, which are having the diameters 10 centimeter, 20 centimeter and 30 centimeters. These are arranged concentrically. So, and the temperatures of the innermost and outermost cylindrical surfaces are 100 Kelvin and 300 Kelvin respectively. Now, assuming vacuum between the annular spaces, find the steady state temperature attained by the cylindrical surface having diameter of 20 centimeter. So what are the things given here? That is epsilon, the value of emissivity for the three surfaces, these are equal and the value is 0.05. So let us move to the next page. So what are the things given? From the given diameter, we can calculate the radius of these three concentric cylinders. That is, the radius will be R1 equals to 5 centimeter, R2 equals to 10 centimeter and R3 equals to 15 centimeter. T1 and T3, these are given in 100 and 300 Kelvin. and the value of the epsilon, that is emissivity, for the three different cases, these are given. It is a 0.05, and we need to find the value of T2 here. This is the steady state temperature for the second cylindrical surface. Now if we refer this diagram for this three hollow thin wall cylinder 1, 2 and 3, so in this case we can write this equation Q12, this will be equals to Q23. So the formula for this two net heat exchange we can write. Now here F12, this is equals to F23, this is equals to 1, and all the epsilons are equal. The value of the epsilon, these are equal. If we put all this value in the earlier equation, then it will be simplified, and in this case A1 by A2, this is equals to R1 by R2, this is equals to 0.5, and the ratio of the areas for these surfaces 2 and 3, it will be R2 by R3, this is coming as 0.67. Now if we substitute the values in the equation 1, so in that case we are having the ratio of the areas and the value of the epsilon we are also having. Next, the temperature for the cylindrical surface 1 and 3 we are having, and the values are 100 Kelvin and 300 Kelvin respectively. So these values, all the values which are given in the numerical, if we put those here in this equation, then after 5 or 6 steps there is a lengthy numerical or lengthy calculation, it is there. So after some steps we will be getting the value of x, which is coming as 2.69, where we have considered x equals to T2 divided by 100. So if x equals to T2 divided by 100, then we are getting the value of x as 2.69. So that means T2 by 100, this is equals to 2.69. The value of T2, that is the temperature of the middle cylindrical surfaces, this is coming as 269 Kelvin. So this is the last numerical of this module that we will discuss today. So for a hemispherical furnace, the flat floor is at 700 Kelvin and has an emissivity of 0.5. The hemispherical roof is at 1000 Kelvin and has emissivity of 0.25. So we need to find the net radiative heat transfer from the roof to the floor. Here the temperatures for these two different surfaces, for the hemispherical furnace and for the flat floor, it is given as 700. For the flat floor it is 700 Kelvin, and for the hemispherical surface it is 1000 Kelvin, and the emissivities for these two surfaces are given as 0.5 and 0.25 respectively. If we write the formula for Q12, which is the net radiant heat exchange from the floor to the roof, because it is written as 12, so the heat will transfer from the floor, from the surface 1 to surface 2, and here it will be this heat will be transferred from the floor to the roof. Now this equation, it is familiar to us, so we can write this equation. Now in this case the area, it is pi r square. A1 equals to pi r square, and A2, this is equals to 4 pi r square by 2. So this is 2 pi r square. Now if we do the ratio of those areas, then we are getting A1 by A2, this is equals to 0.5, and F12, that is the configuration factor for these two different surfaces, this is 1. If we put these values and the other values that is given in the question, then after some steps we are getting the value of the net radiant heat exchange. This is equals to minus 12,310.4 watt per meter square. Now here we are getting Q12, that is the heat exchange from the floor to the roof. This is negative. So if this is negative, so this negative sign, it indicates that the floor is gaining the heat. As Q12, this is negative, so that means from 1 to 2 it is negative, that is from the floor to the roof it is negative. So ultimately the floor is actually gaining the heat. This is the physical significance of the negative sign in this numerical. So we can write this answer in this way also, that is Q12 equals to the positive magnitude, that is 12,310.4 watt per meter square. But if we use this positive value, then we should write that the fluid is gaining the heat from the cylindrical hemispherical part, spherical surface. That gain term should be there if we use the positive value of the result. So this is the end for this lecture.